This is lesson 4 of the Functions and Graphs chapter, and this is concerning inverse functions, so we're going to be going backwards today. So if we think of a function as a mapping, we're going from x to y via the function f. So to go from y to x, we need to do the inverse. So an inverse function, f to the minus 1, does the opposite of the original function. So if my original function was acting on the number 4 and I got the output 2, then my inverse function, when acting on the number 2, would give me the output 4. So I'm going to look at the function f of x equals 2x plus 1. And we're going to go back to year 7 with our function machines. Unfortunately, I'm not drawing the nice function machines, they're ovals. We've taken the input x, we've multiplied it by 2 to get 2x, we've added 1 and we've got 2x plus 1. To do the inverse, we're just literally going to pull the whole operation backwards. We're going to take off 1, then divide by 2, and that will get us back. So f to the minus 1, or the inverse of x, is x minus 1 all divided by 2. So this has appeared in the exam before, why the function must be 1 to 1 for an inverse function to exist. So have a few seconds of thinking about 1 to many and many to 1, and then we'll look at the answer. Okay, so if we think about it, if the mapping was many to 1, then the inverse mapping would be 1 to many. And 1 to many is not a function. Therefore, it must be a 1 to 1 for an inverse function to exist. So, in the original function, we have the output y in terms of the input x. Y equals 2 times x plus 1. So if we change the subject to get x in terms of y, then we have the input in terms of the output, i.e. we've got the inverse function. So all we need to do is rearrange the function to get x in terms of the output. So we write the function down in terms of x. So we'd write f to the minus 1 of x is x minus 1 over 2. So what we've done is we've taken our function, we've changed the subject to the function so that x now is the subject. Then we've rewritten it, replacing the y by an x and putting function notation at the start. And that is how we find the inverse function. So let's look at a few examples. At the top of this slide, I've placed a summary of the last slide. So if f of x is 3 minus 4x, find the inverse function. So the first thing we do is we write y down instead of function notation. And that's just for convenience. We're not doing it for any other reason. Then what we're going to do is we're going to rearrange the function to make x the subject. So that's what I've done here. Finally, we're going to tidy up the notation. So we're going to write it, the function, in terms of x. So f to the minus 1 of x is 3 minus x all over 4. So replacing the y's with the x at the end. So let's have a look at another one. This one looks a little harder. So f of x is x plus 2 divided by 2x minus 1. X can't equal a half because otherwise we'd end up dividing by 0. We want to determine the inverse function. So we have a 3-stage process. Our first stage is to write it in terms of y. So we actually haven't done any thinking, we've just rewritten the question out in terms of with a y. Our next stage is very simply to rearrange the function to make x the subject. So we rearrange it, and this has taken us several lines, and I'm not going through line by line. I expect you to understand that. If you don't, stop, have a look, and look at exactly what I've done. So we've made x the subject. Last but not least, we need to rewrite it out in correct function notation. So the inverse of the function x is x plus 2 divided by 2x minus 1. Which is quite an interesting function because all we've actually discovered is the function is self-inverse. which does sometimes happen. It's rare, but it does happen. You get what's called a self-inverse function. So now we're going to look at graphing an inverse function. So what an inverse function effectively does is it swaps your x coordinates for your y coordinates. And you can think of it as basically swapping your x and y axis around. So you end up creating a reflection. So the domain of f of x is the range of the inverse function, and the range of the original function is the domain of the inverse function. So let's look at this red function y equals f of x, the red line, and you'll notice there's an asymptote at x equals 1, and the domain of f therefore is x is greater than 1. So the range of this function is going to be x is greater than 1. So it really is as simple as that, and we swap them both round. Notice as well that this graph is effectively a reflection. That line y equals x is a line of symmetry. So the graphs are symmetrical, and normally when you draw these type of graphs you would normally put in the symmetry line. So let's look at an example now. This comes from the textbook. If g of x is defined as g of x equals the square root of x minus 2, where x is a real number and it's bigger or equal to 2, it can't be less than 2 because that would make this a square root of a negative number. And as x is in the real set of numbers and they're no complex, we've immediately got rid of that potential. So the range, thinking about that, is going to be f of x is greater or equal to 0. Because when you put 2 in there, you're going to get the square root of 0, and the square root of 0 is 0. So now we want to find the inverse of the function. So remember what we do to find the inverse. First we write our function out in terms of y, then we rearrange to make x the subject, then we sort out the notation. So this means start with y equals x minus 2, we then rearrange, so the function g to the minus 1 of x is x squared plus 2. So the next one is sketch the graphs of both functions. Now, normally you'd sketch the graph of one function, put in your reflective line, and that would then help you sketch the graph of the other function. And you normally pick off the one that you find easiest to sketch, which is why at one stage I said learn the common functions and what they look like. So this would give you something like that, and I would definitely put my y equals x line in here. State the domain and range of the inverse function. Well, the domain of the inverse function is the range of the original, and the range of the inverse function is the domain of the original. So all we have to do is swap round our original answers. So when we got the range of g of x, that now becomes the domain of the inverse. The range, we go back to the domain of the original. Okay, let's have a look at another example. This is also from the textbook. And we have a function that's defined by f of x equals x squared minus 3, so a very simple quadratic. X is in the real set of numbers, and we've defined the domain of x to be greater than or equal to 0. Now normally we wouldn't bother to define it, but we want to find an inverse. That's the first part of the question. And if we don't define that domain, we take a many to one function and turn it into a one to many, and the inverse would be a one to many, which is not a function, so we're restricting the domain to a one to one. So to find an inverse, remember what we do. We set y equal to our function, our x squared minus 3. We then rearrange to find x, and then we sort out the notation, which means we turn the y's into x's, and where there's an x we put function notation. So y is x squared minus 3. So x is the square root of y plus 3. And then we've got our function notation and the square root of x plus 3. Now then we've got sketch y equals f of x and y equals the inverse of f of x, f to the minus 1 of 8, and state the domain of the inverse. So when you come to sketching, I would pick the easiest functions to sketch. I would draw y equals x in, and then I would mirror it to see what it looks like. And you should know, both of these functions should be well known to you anyway. You should know what a square root function looks like, and you should know what a quadratic looks like, so it should not be difficult. But these are ones you need to really learn. So when we come to draw, my original function is in red. And there is my quadratic function, translated down 3. I put in principal points where it crosses the axes and meets axes. This is partly in the case of the root 3 there. It's not needed, but it just makes me feel better to have principal points in. And I think you really should put principal points in. And often the examiner will take a mark off if they're not there. So I put my reflected thing in, my reflected function here, my inverse. And this crosses, it meets at minus 3. So if you look at the domain for this, the domain was x had to be greater or equal to 0. The range, well, it starts at minus 3 and it heads off to infinity. So our range for this will be y is greater or equal to minus 3, which gives us therefore our domain for our inverse function, x is greater or equal to minus 3. Then it says solve the equation f of x equals the inverse of x. Now if you try and solve that by setting x squared minus 3 to the square root of x plus 3, you are going to have, well, you can do it. I mean, I tried for about 3 seconds and decided that was far too hard. There had to be an easier route, because this is A level, this is not some sort of marathon evilness. There is a third line there, y equals x. Both of those lines, if there's an inverse, if you can solve the equation, they must meet on that line, y equals x. Therefore, if you set the line y equals x to y equals f of x, if you set those two lines to be equal, you will find the point where they meet, because it will automatically be the point where the other one meets. So x squared minus x equals 3, because that's where they meet. And x squared minus x minus 3 has got to be 0. And therefore, you can solve that and you can use your quadratic formula, and you can see you only want the positive solution. And apparently there was once an exam question based on this principle. So that the trick here is to say, well, actually, if I make the inverse equal to the actual thing, I'm going to get an equation that's foul. Is there something easier I can do? And the something easier I can do thought separates from the mathematician than those who just learnt it by rote. You've got to look at it, analyse it, and think, can I do something else? So that takes us to testing our understanding with an exam type question. So my function f is defined so that f such that x maps onto e to the x plus 2, and x is a real number. I want to find the inverse of the function f, stating its domain, and on the same axes sketch the curves with the equation y equals f of x and y equals the inverse, giving the coordinates of all points where the curves cross the axes. So to find my inverse, I'm going to set my y equal to e to the x plus 2. I'm going to rearrange, y minus 2 is e to the x, and then that gives me ln brackets y minus 2 is x. And I haven't, so again, that gets me a mark. My rearrangement gets me a mark. My second mark comes from writing correctly in the notation, in proper function notation, and I now have to state its domain. Well, with a ln, you cannot go below 0. You can't take a ln, you don't have negative lns, so therefore x has to be bigger than 2. So now let's look at the graphs. Again, I would get my calculator to do this, and I would put in my asymptotes, and my asymptotes here are x is 2 and y is 2. It crosses the graph at 3, 0 and 0, 3, because when you put e to the 0 you get 1. Don't forget that. It doesn't cross at 2, it crosses at 3. So you get your general shape. You don't have to put that nice reflective line in, but boy does it help. And you're going to get marks for, again, putting your principal points in. Okay, so this leads us to doing exercise 2D, pages 38 to 39. Thank you.